Ladies and gentlemen, I was ready for this problem, and I mean that in the sense of I had some good utilities set up that made it very easy to solve day 12 of Advent of Code. We can see we've got another sort of 2D problem, but this is now a 2D search problem. So what we're doing here is we're trying to navigate from the S position in this 2D grid of characters to the E, but the letters all correspond to heights. So we can sort of think of them as the heights, 1 through 26, Z being 26, A being 1. S has the height of A, so it has the lowest height, and E has the height of Z, so it is the highest height. And the reason the heights are important is that we can only move from one location to the other. We can always go down, so we could always go from, say, this Q down to this R, or the Q down to the B, but we can only climb up by a height of 1 each time. So what does this mean? We can go from A to B, and we can go from B to C, but we cannot go from B to Q, because that's too many steps. So we want to find the shortest path from the start location to the end location, but we're restricted in how we can take that path. But there's no cost per se for each step we take, or it's a flat cost. So this is a breadth first search problem with the various restrictions we have on where we can move. And the good news is that I did several articles on Dijkstra's algorithm earlier this year, and I eventually came across the algorithm.search library that provides some nice helper functions for doing these kinds of problems, and it also includes a BFS monadic search function. So I will be applying that. We'll come back to this type signature when the time comes, but first we want to make sure that we're parsing our input properly. So there were a couple helpful utilities for this. So I had to modify my existing utility for parsing a 2D digit grid and just make that a 2D character grid. That was fairly simple. I still have to revise this function because it's no longer just digits, but we can now get a character in an array. So that parsing is pretty easy. We have to do a little bit of post-processing on the grid that we parse because we want to reassign that S value to have the height of A, and we want to reassign the N value to have the height of Z. But we also want to save that start and that end value so that we can reference them later. So how do we do this? Well, we get all of the associated pairs in the array that we've parsed. We find start, we find end, we expect them both to be just, and then we use this array operator to effectively modify that array so that we place A back in the position of the start and Z back in the position of the end, and we return our new grid along with the start and end coordinates. That's our input type. Once we have those, now we want to invoke our call to BFSM. Now there are 3 arguments to BFSM. Let's go back to the documentation. So the first one is that's where most of the complications are. We need to take a particular state and generate the list of new states that we are possibly going to. This is the possible neighbors list. The second argument is our end condition. So when have we reached the end of our maze? And the third is the initial state. So what we're going to do is we're going to treat the state as the current coordinate we are in this search. So obviously, the start. This is the third argument we're going to provide to BFSM. The second argument is going to be it's very simple as well. We will return as long as the coordinate we are on is equal to the end coordinate. Now, where does all the logic happen? The logic happens in this, the valid moves function. So this, we're going to parameterize it by the grid we receive. This is effectively a constant. So as far as the algorithm is concerned, this is the type signature. We take our current state, the coordinates, and we return a list of possible coordinates that we can move to. How do we do this? Well, first, I have another 2D grid utility, get neighbors. So this takes a 2D grid, it takes a coordinate within that grid, and it just returns for us all of the neighbors. This is 4-directional. I have a different one for 8-directional, but with 4-directional, we're just looking up, down, left, and right, and we're just doing bounds checking. That's most of what this function is doing, is making sure that we don't go out of bounds. So that allows us to narrow our search to just sort of up, down, left, and right. But we want to apply one more filter. We'll have this neighbor test. And so we take the current height by obviously looking at the grid values. And we also want the new height. So when we're evaluating a possible neighbor, we look at its coordinate, we get the coordinates height, so we call that new height, and then we use OR to compare these as numbers. And as long as the new height minus the old height, or current height, as long as that is less than or equal to 1, then we're able to make this move. So we return just this filtered list of the possible neighboring coordinates. We provide that as the first argument to BFSM, and we just get our results. This will just give us a list of paths. It will return nothing if we can't find a path, so we'll return, we just want the length of that path, so we'll return max bound. If we're getting nothing there, as long as we get a path, we just return the length of the path. So that is fairly straightforward. So the test case I found in that, my larger case, I had a path length of 449. Easy enough. So now moving on to the hard part. The hard part is not that much harder. Really, we're just going to look at every possible location that starts with A. So we're going to take our grid and we're going to filter by all the different locations that have A as their start. And we just want to find all of the shortest paths of every location that starts as A and just return the length of the shortest one of those. So we just map our previous function, process input easy. We're reusing that here to get the shortest path from each of these possible start positions. We get our results, we return the minimum of the results. It's actually very simple as long as you have the core parts of the 2D algorithm. And we combine it together very easily. So what I found in my test case, the original start location had a path of 449 to reach the end, and coming from a different A location is able to get 446, and this is the large grid I had. So we can sort of see some of the contours in this grid, even if it's not perfectly. We have a lot of, A's can't make it up to the C's, so there are some places you can get stuck in this grid, but this is the end. We can see its height sort of grow. So that's kind of interesting. But yeah, that's pretty much all there is for this problem. Pretty simple if you have the right utilities and if you have experience with these kinds of problems. So we are now just about halfway through Advent of Code. So come back tomorrow. We'll have another video for you. And subscribe to the YouTube channel. Subscribe to Monday Morning Haskell mailing list. That link is in the video description if you're really enjoying this content. So thank you so much for watching, and I'll see you tomorrow.